Welcome to the Predictive Analytics for Marketing course. My name is Dr. Ash Pahwa, and this is lesson 2. Here we are discussing data central tendencies and variabilities. Now, in the previous lesson, which was lesson 2.1, we covered data, variables, and samples. Then, after that, in lesson 2.2, we covered displaying and summarizing data. So this is now lesson 2.3. Here we are going to discuss numerically summarizing data. So this is the outline of this lesson. We are going to start this lesson with the measurement of central tendency. So here we are going to cover mean, median, and mode. Next, we are going to cover the measure of dispersion. It means how much amount of variance do we have in the data. So this covers range, variance, and standard deviation. Then we're going to cover the empirical rule, which is the standard normal distribution curves, the standardized values, and the standard normal distribution. Next, we're going to cover the measure of position. So in this, we're going to cover z-scores, percentiles, and quartiles. Then we look into the 5-number summary, which is also called the box plot. And in the end, we're going to cover the data normalization issues, which is standardization and scaling. So let us begin with the measurement of central tendencies. When we have data, we have the opportunity to compute these metrics. This includes the data's mean, median, and mode. First, we will define these terms and examine some examples of each one of them. So now let us start with mean. Mean is one of the most common metrics. It is used not only in statistics, but in our daily life as well. I'm sure each of you are familiar with the metric called average. We basically add up all the numbers and divide the total by the number of observations. Whenever we compute the mean for a population, it means for the entire set of people or entire set of objects what we call as a population, as the mean of population is being represented by the Greek character mu. Now suppose there are total n observations. Then in that case the mean of the population would be expressed as x1 plus x2 all the way till xn, then divided by n. Now, whenever we take a sample, computing the mean of a sample is the same as the processing of the computing the mean of a population. But in statistics, we usually write the mean of a sample as x bar. Suppose x is my variable, then the sample mean is being represented as x bar, whereas a population mean is being represented by the mu character. So in a sample mean, again, we add up all the numbers and divide the total by the number of objects that we have in our sample. So that is the mean of a sample. Let us take some actual data and compute the mean. Suppose I have the test scores of certain students. Suppose I have 11 students in my population and their scores are 82, 77, 90, 71 and so on, as you see displayed in this table. So the mean, which is mu, is equal to 82 plus 77 plus 90 all the way till 96. So if we add all these numbers up, the total comes out to be 886. And since there are 11 observations, we divide 886 by 11, which is equivalent to 80.5. We can also compute the mean on a spreadsheet, or we can use a simple calculator. Now let us look into the second metric, which is called median. Median basically means the middle number. So to find out the median, we sort the data in ascending order and the middle number is the median. However, if the number of observations we have is odd, then we can select the middle number and that would be n plus 1 divided by 2 position. In the next slide, we are going to demonstrate this. Suppose a number of observation is even, then we are not going to get a single number. We are going to get two middle numbers because the total number of observation is even. So we need to compute the mean of those two middle numbers. So it seems the mean of n over 2 position and n over 2 plus 1 position. So in the next slide, we are going to take an example of this. So let us revisit the data that we used before. As you recall that we have 11 students and the total number of observations are odd. We can take the middle number, and the middle number of course is going to be number which comes in the 6th position. First we have to sort this data. Now the sorted data would be 62, 68, 71, 74, 77 all the way till 96. The middle number of course is going to be n plus 1 over 2 position. Since n in this case is 11, so 11 plus 1 is 12 and 12 divided by 2 is 6. So the 6th position number is 82. This then is the median of this particular data set. Suppose now the number of observations is an even number instead. Suppose we have 10 observations. Then there are going to be 2 middle numbers. So to compute the median, we take these 2 numbers and we compute the mean of them. We take the n over 2 position and n over 2 plus 1 position. Since n in this case is 10, so 10 divided by 2 is 5th position or the 6th position. So if we sort the data, our 5th position data is 77 and the 6th position data is 82. So the mean of 77 and 82 is 79.5. So that is how we compute the median when the number of observation is even. We have covered 2 different metrics, mean and median. So what are the advantages of one over the other? Mean and median will give us approximately the same numbers if the data is normally distributed. But suppose we have some outliers. In that case, the median is not going to change significantly. The mean, however, will change. For example, suppose we have these 11 observations on the number of minutes of calls. The numbers are 1, 2, 3, 7, 4, 5, 4, and so on. So the mean of these numbers is 3.5 and the median can be computed very easily and it comes out to be 3. Now suppose if we have an outlier. Suppose one of the phone calls is 48 minutes long. So in that case, let us try to compute the mean of these numbers, which comes out to be 7.3. So as you can see, the mean jumped from 3.5 all the way to 7.3 just by adding one observation. And then, however, the median of these same 12 observations has changed very slightly from 3 to 3.5. So median does not change very much in case of an outlier. Whenever we are dealing with real world data, we often have a few outliers, and that means that the value of those variables are either too large or too small. So generally we ignore outliers, but if we choose to use them, the median is a better metric. Now let us look into the third metric, which is mode. The mode of a variable is the most frequent observation of that variable occurring in the data set. So suppose if we have a data set in which zeros are occurring 11 times, then 4 ones, 1 twos, and 1 threes. The mode in this particular data set is going to be 0 because 0 is occurring very frequently. So in data sets such as these, where there's a lot of repeat thing happening, it is a good idea to examine the mode. Mode basically gives the data value which is occurring most frequently in the data set. So far we have discussed the measure of central tendency. Now let us move on to the next issue, which is measurement of dispersion. This means we will be looking into variance, how much the data differ from each other. To do this, we employ 3 different measurements. One is called range, the next one is called variance, and the third one is called standard deviation. So now let us examine each one of these 3 metrics. First, let us define range. Range is very simple. It is the largest data value that we have in our data set minus the smallest data value. It is very easy to compute these numbers, so we simply sort the data, then pull out the data which is the highest value and the lowest value to determine the range of the values. The difference between the highest and the lowest is the range. For example, using the same data set that we had before, the test scores of certain students. Now, if we compute the range of this data, we can see that the largest data value is 94 and the smallest data value is 62. So, the range of this particular data set would be 94 minus 62, which comes out to be 32. Now, let us look into the next metric, which is variance. So, to define the population variance, it is the sum of the squared deviation above the population mean divided by the number of observations in the population. First of all, we need to compute the mean of our data set. Suppose the mean is mu. The variance would be defined as sigma square, where sigma is a standard deviation, and we will be talking about that right after variance. So, sigma square is x1 minus mu whole square, x2 minus mu whole square, and all the way till xn minus mu whole square. So, we compute the deviation from the mean, then square them, then sum all the numbers, and finally divide this figure by the total number of observations. In the next slide, we will see an example of how we can compute the variance of a data set. So, here is our data set. This is the same one we used to compute the mean and also the range. We have the scores of all the students. First of all, we are going to compute the mean, which, as we have seen before, is 79.0. Next, we compute the deviation from the mean for each and every value in our data set. So, let us start with the first one, where the score is 82. So, 82 minus 79 comes out to be 3. That is the deviation from mean. Next, we square this number, because if we only add all the deviations, they will come out to be 0. So, this is because there will be some positive deviation and there also will be some negative deviation. In order to find out the actual value of the deviation, we square these numbers. The square of the positive number is positive, as is the square of the negative number. Both are always positive. So, the squared deviation is always going to be positive. So, now let us take the second data set. Here the data value is 77, and since the mean is 79, the deviation is minus 2, and the square of minus 2 of course comes out to be 4. If we repeat this process for the entire data set, then the sum, and then we sum the squared deviation. So by adding all the squared deviation, we get 964. Since the total number of deviations that we have is 10, then the variance of our data set comes out to be 96.4, which is computed by dividing 964 by 10. Now let us compute the variance of a sample. A sample variance is defined as the sum of the squares deviation about the sample mean divided by the number of observation in the sample minus 1. So, here in our example, we divide this by n minus 1, whereas in the case of a population, we were dividing it with n. That is the only difference between them. And the reason we are subtracting 1 from it is because of the degree of freedom. Degree of freedom means the total number of observations minus the total number of variables. Since we have only a single variable here, the degree of freedom in this case comes out to be n minus 1. So that's why we divide it with. In this way, we define the variance of our sample. Now let us define the standard deviation. The standard deviation of a population is the square root of variance. We defined our variance as the Greek character sigma. So the sigma square is the variance. If we take the square root of sigma square, we are going to get, of course, sigma. So sigma basically comes out to be the square root of variance. While computing the variance, we were squaring the difference between the data and the mean. Therefore, while calculating the standard deviation, we undo the effect of square. That's why we take the under root of variance to measure the true deviation of the data from the mean. We can also define the standard deviation of a sample, because we computed the variance of our sample as s square, and obviously if we are going to take the square root of s square, we are going to get s. S is being used as a character to denote the standard deviation of a sample. In the next slide, we are going to use an example of computing the standard deviation. Now let us compute the standard deviation of the population. As you may recall, we saw this particular slide before, and we computed the variance of this data, which came out to be 96.4. So if you want to compute the standard deviation, we take the under root of 96.4 and we are going to get the value of 9.8. So 9.8 is the standard deviation of this particular data set. Next, we will examine the empirical rule. Empirical rule shows us the distribution of our data. Most of the real world data that we get is usually bell-shaped curve, which is also called the normal distribution. For example, if you look into the height of people, you're going to find this thing to be a pretty normal distribution. We find that the average height of an American male is approximately 5 feet 11 inches. Of course, we are going to see a lot of people with height of more than 7 feet and also a lot of people with a height of less than 5 feet. By drawing this histogram of this data, we will see that the shape of our data is indeed bell-shaped. So we will explore this bell-shaped curve next. Real world data usually have the type of bell-shaped pattern we have just seen in this histogram. It is showing us the frequency of data. Now in the center we have average, and we learned the mean of the data for the population is called mu. So mu is right on the center line. Now if we go one standard deviation above the mean, it will represent 34% of the data. And if we go one standard deviation below the mean, we are going to get another 34%. So if we take the data from mu minus sigma through mu plus sigma, that will represent 34 plus 34, that comes out to be 68% of the data. Now if we go 2 standard deviations on the left hand side and 2 standard deviation on the right hand side, we will get to 13.5 additional data on the left hand side and also on the right hand side. So then if we add all these numbers up, that comes out to be 13.5 plus 34 plus 34 plus 13.5, which comes out to be 95% of the data. Now if we select 3 standard deviation below the mean and 3 standard deviation above the mean, then we add up 2.35 on the left hand side and also on the right hand side. Our total comes out to be 99.7 of the data, which is within 3 standard deviation of the mean, which is mu minus 3 sigma to mu plus 3 sigma. So this is the way our data is being distributed. This type of curve is also called normal distribution. Most real world data will fall into this category, but there are certain real world data that may not fit into this category. It may have a uniform or a Poisson distribution. There are various other types of distribution, but most data will fall into normal distribution curve, which we refer to as the empirical rule. So this empirical rule, we have almost 68% of the data between mu minus 1 sigma to mu plus 1 sigma. And then 95% of the data is mu minus 2 sigma to mu plus 2 sigma. And 99.7% of the data falls between mu minus 3 sigma to mu plus 3 sigma. These percentages are very important. Later on, when we look into the hypothesis testing and compute the inference data, this particular chart will become very useful. Now let us examine the next topic, how to compute the standardized values. These are also called Z-values. The major advantage of computing a Z-value in data distribution is this. If we assume the population has normal distribution, then we can very easily compute the probabilities of certain events. So now let us start by understanding the definition of Z-value and also related P-values. Z-values are also called standardized values because assuming our data is normally distributed, a Z-value indicates that it's going to fall into that empirical rule or that bell-shaped curve that we just saw. So the purpose of computing the Z-value is that we can compute the probabilities of certain events. Let us start by defining what a Z-value is. Later on, we are going to use an example to compute probabilities. The Z-value is defined as data value minus the mean divided by the standard deviation. If my Z-value is 2, basically it means that the data value is 2 standard deviation above the mean. Another example is that if the Z-value is a negative 1.6, it means that the data value is 1.6 standard deviation below the mean of the data set. Now let us define the p-values. P-values represent the area under the normal distribution curve toward the left hand side. So how do we compute the p-value if our z-value is 1? With a z-value of 1, it means that we have 1 standard deviation above the mean. So what is the area size on the left hand side of 1 z-value? To determine this, we will add these values, which are 0.15 plus 2.35 plus 13.5 plus 34 plus 34. So it comes out to be 84. It means if our z-value is 1 standard deviation above the mean of the data, then there is 84% of the data which is below that value. So that 84% is the area under the curve on the left hand side. That's why 84% of the area is being displayed in red color. If we add all the area under the curve from z-value of -3 to +3, that of course is going to be 1. And that represents the probability of certain event, which is going to be maximum as 1. This basically shows the area under the curve shows the probability of certain event. In our example, for z-value of 1.0, our p-value is 84% or 0.84. So for a given z-value, we can now compute the p-values. P-values are always going to be the area of the curve. Suppose our z-value is 3, as you can see right on the graph, which is on the top left. Everything covered with the red except for a very small tip, which is going to be on the right hand side. So the area under the curve is equivalent to 99.87%. So the p-value is going to be 0.9987. Now if we take the z-value of 2, then the area that you are going to see in the middle top graph is going to be 97.72%. So the p-value is going to be 0.9772. Now again, if we take the 1 standard deviation above the mean, which is considered to be z is equal to 1, then the area is going to be 84.13. We saw this in the previous slide that the area is going to be 84. If the z-value is going to be 0, that will be right in the middle. So it means that there is 50% of the data is on the left hand side and 50% of the data is on the right hand side. So the p-value of course is going to be 0.5. Again, if our z-value is going to be a -1, then the p-value is going to be 0.1587. If our z-value is going to be -2, meaning the p-value is going to be 0.0228. Finally, if our z-value is going to be -3, then the p-value is going to be 0.0013. Now let us take an example and see why these numbers we have computed of z-values and p-values are so important and are so useful as we begin to compute the probabilities. But first, let us ask this question. What is the probability that a randomly selected student will have a SAT score between 450 and 600? Here we have a population of students and the mean is 500, and we will say that the standard deviation is 100. We need to know the probability that a student will have a SAT score between 450 and 600. So we compute the z-values, and from these we can compute the p-values. So as you can see, we can compute for the first point, which is 600. So our z-value is going to be 600 minus 500 divided by 100. This is so because 600 is the actual data value, 500 is the mean, and 100 is the standard deviation. Our z-value comes out to be 1, and the p-value that corresponds to z-value 1 is 0.8413 that we saw in the previous slide. Now let us compute the second point, which is 450. The z-value is 450 minus 500 over 100, which comes out to be negative 0.50. The corresponding p-value is 0.3085. Next, we want to know what is the proportion of z-scores between 600 and 450 happens to be. To determine this, we simply subtract 30.85 from 84.13. The answer is going to be 53.28. So we can assert that almost 53% of the students are going to end up with a SAT score between 450 and 600. This should enable you to see how useful these numbers are. However, we are assuming that the data that we have about the student scores is normally distributed. So based on that assumption, we can successfully manage to compute these probabilities. We can show the same data using a graph. By drawing our empirical rule bell-shaped curve, we can display the area which is between 600 and 450. But we need to determine the probability that is a randomly selected student will have a SAT score between 450 and 600. So we compute that number to be 53.28. Now, if you want to display this data using the bell-shaped curve, we can draw this particular area in red color. So the area under the entire curve is 1. So this red-shaped portion that you are looking at it in the graph is 53.28% of the total area. That represents the total probability. So using z-scores and p-scores, we can compute these numbers very easily as a useful way to measure the probabilities and to display that data using the empirical curve. So far we have seen the normal distribution curve. Now we are going to look into the standard normal distribution curve. The only difference between a normal distribution curve and a standard normal distribution curve is that in standard normal distribution, my mu or the mean is 0 and the standard deviation is equal to 1. So based on these two specifications, we can draw the empirical rule graph, and that becomes the standard normal distribution curve. So here is the plot of my standard normal distribution curve where mu is equal to 0 and sigma is equal to 1. So in this case, when we have the standard normal distribution curve, the mean is equal to median is equal to mode, which occurs at z is equal to 0. So right in the center is the mean, which is 0, median is also 0, and mode is also 0. And the inflection points are +1 and -1. And the area under the curve is 1. And the area on the left, which means that where the value of mu is 0, so the left part of it is equal to the area to the right part of it. And of course, it follows the imperial rule that that within one standard deviation, it's going to have 68% of the data, and two standard deviation is going to have 95%, and three standard deviation is going to have 99.76% of the data. In most of the statistics books, you will find this table which is called the standard normal table, and usually it is given at the end of the book. And what you see in this table are the p-values. So p-values are the probabilities. So earlier, when we did not have the calculators and computers, people used to use these tables to do the computation. But these tables are not very precise. Because they can only give you some numbers between certain intervals. As you can see, when the z values are 0, 0 or 0, 1. What if the z value is in between these two numbers? So that is the reason why the standard normal tables are not very precise. So now, of course, these days, very few people use standard normal tables because these values are built into all calculators, all statistical tools like Excel and R and Python, and so that is the reason why these tables are not being used. But these tables basically represents the z values and the p values. So I'm going to show you now some formulas which are available in Excel to compute the z-values. So this formula in Excel is called standardize. So in the standardize, first of all, we feed in the value that we want to, for which we want to compute the z-value. Then we feed in the mean and then the standard deviation. So let's take this curve here that you're looking at it on the right hand side. Here my data, let's assume, is 110. And I have to compute the z-value, and the mean is given to us as 100 and the standard deviation is given to be 15. So in Excel I'm going to say standardize. Then I have B5. As you can see, in B5 I have this 110, then B2 which has the mean, and B3 has the standard deviation. So I get the value of 0.6667. So that is my z value for this data element of 110. So once I've given the z value, I can also compute the p value. So what is p value? As I said before, is the p value is the area under the curve which is on the left hand side of that z value. So suppose if my z value is 0.21, in Excel I can compute this number, which is norm s dist. Norm s dist basically means normal standard distribution, and then I feed in which is my b4. B4 I have the z value, and I'm going to get the p value. So the p value is 0.5832. So it means this red portion is 58% of the entire area. So that is basically what the p-value is. So in Excel, of course, we use this function called norm s dist. And you can also use the standard normal tables, which are usually printed at the end of most of the statistics book, but those tables are not very precise. So that is the reason we use these functions which are available in Excel. In fact, these tables are also built into many statistical calculators as well. So you can compute this number either using a calculator, Excel or R or Python or any other tool which will allow you to compute these numbers. So now suppose my z value is 0.21, and if I want to compute the area on the right hand side under the standard normal curve, since I know the total area under the curve is 1, and also I have the ability to compute the area on the left hand side of that z value. Now, if I want to compute the area on the right hand side, so we just take 1 minus the area on the left hand side, it will be equal to the area on the right hand side. So let's take a very specific example. If my z value is 0.21, the area on the left hand side, it is 0.5832 that we saw in the previous slide. We can get this number from norm s distribution by feeding the value of 0.21. So now the area on the right hand side is going to be 1 minus norm S distribution of B8. B8 of course is my Z value. So my Z, which is 0.21. So 0.4168 is the area on the right hand side. So 58.32% of the area is on the left hand side and 41.68% of the area is on the right hand side. And of course, if you add 0.5832 with 0.4168, that will come out to be exactly 1. Now suppose if I want to compute the probability in between two Z values. So my Z values are Z1 and Z2. So I'm going to compute the area on the left hand side from Z1, and then also I'm going to compute the area on the left hand side of Z2. And if I subtract these two numbers, if I take the difference of these two numbers, then I'm going to get the area in between. So let us take a very specific example. If my Z value is plus 0.31 and my Z2 value is minus 0.31. So what is the p-value in between these two Z values? So I use this formula of norm S distribution B12. As you can see, B12 I have got the value of Z1, which is 0.31, minus norm S distribution of B13, and B13 contains minus 0.31. So the area in between these two Z values is 24.34%. Now suppose you are given the p-value and you have to compute the z-value for that. It means you are doing the inverse of that. So your p-value is being given to you. So suppose if my p-value is 0.58. So now what is the corresponding z-value for that? So there is a function available in Excel called norm SINV. INV stands for inverse. So the inverse of that function is my z-value, which is 0.2019. So if my p-value is 58%, if this value is being given to me 58%, which is shown by the red color in my graph, then what is my z-value? So I can compute using the normal standard inverse function. So this way, from z-value I can compute the p-value, and from p-value I can also compute the z-value. So here are some of the Excel functions that I talked about. So this is just a summary of everything which I've covered. So that is a function called standardize, which is going to take the mean and the standard deviation and give you the z-value. From z-value, I can use norm S dist function to compute the p-value. And if my p-value is being given to me, if I want to compute the z-value, I use norm S INV function. So these three functions are used very frequently in Excel to compute the z-values and also the p-values. So these functions are also available in all statistical tools. Excel is one of them that we are going to use primarily in this course, but if we are planning to use R, these functions are available as pnorm and qnorm. And again, they work exactly like the Excel functions. Similarly, in Python or in any other statistical tool that is available to us, these two are very, very common functions that are used to compute the z-value and the p-value, and we can compute the p-value from z-value and from and also the z-value from p-values. So we can go from z to p, p to z using these functions. So these are the R functions. As I said before, scale is a function that will give you from value to z value, and p norm will give you the p value from z value, and q norm is going to give me the z value from p values. So these functions are used in R. So now let us look into the last portion of this particular lesson, which is about percentile and quartiles. Now let us start with percentiles. The kth percentile of a set of data is a value such that kth percent of the observations are less than or equal to the value. Now suppose we have this data. We sort it out and plot the histogram. The bottom 1% of our data represents the first percentile, and the bottom 2% of the data is being treated as a second percentile. Similarly, if we go on the other extreme, The top 1% is considered to be the percentile rank of 99, and the top 2% will be represented as the 98th percentile. So percentiles are a very useful concept. We use them primarily to show where in this entire spectrum the subject of our data fits in. The order in which our data appears allows us to see exactly where this data belongs in the entire data spectrum. Next, we are going to discuss quartiles. Quartiles are very similar to percentiles. The only difference in quartiles and percentiles is this. Quartiles only divide data into 4 different categories. So the first quartile, which is also called Q1, represents the first 25% of the data. In this category, we have 25% of the data, and then that data which is on the top of the first quartile will be 75%. The second quartile basically comes at the median. Half of the data is going to be lower than the second quartile, and half of the data is going to be higher. The third quartile represents 75%. It means that the bottom would be 75% of the data and the top is going to be 25. Fourth quartile, of course, represents 100%. The bottom is 100% and the top is 0%. So when we divide the data into 4 different categories in our histogram, then we call them quartiles. Now let us examine the box plot. It is yet another way by which we can present our data. Suppose our data is a bunch of some random numbers. The minimum is 19.95 and the maximum is 54.63. If we compute the median of this data, it comes out to be 30.95. Next, we will determine that the first quartile comes out to be at 26.06 and the third quartile comes out to be 37.24. Now we can draw this as a box plot. Our box plot, the way we show it over here, is a box in the middle, and on the top or the top line represents the third quartile. So as you can see, the top edge of this box comes out to be around 37.24. And the bottom edge is the first quartile, which is 26.06. Now if we draw these whiskers basically means the maximum and the minimum value of the data. So the maximum value comes out to be 54, and in this particular case it is treating 54.63 as an outlier. So 54.63 has been plotted as a dot, and then the maximum value of this particular diagram is showing somewhere around 49 and the minimum is 19.95. So this box plot is sometimes an easier way to see what our data ranges are and how it is distributed. So box plot is a very common way to display and view the data. Now let us look into how we can normalize the data. There are 2 ways by which we can do the normalization. One is called the standardization, other one is called scaling. In a standardization, the values can vary from -3 to +3, which are the Z-values that we talked about a few minutes before. But in the case of a scaling, we can scale the data from 0 to 1. So there are 2 ways by which we can normalize the data. So the first question is that why should we standardize, or why should we normalize, or why we should scale the data? The reason we do this thing in statistics and also in predictive analytics is that when we have 2 variables and if they have a different scales, then in that case that variable which has a very large scale will start dominating the model. So we have to bring all of my variables into the same range. And no matter which modeling method we use these methods. So let's take a very specific example. Now suppose the height of people vary basically between 4 and 7 feet. So as you can see, the variation here is only up to 3 feet. But as far as the net worth is concerned, it can vary from 10,000 to all the way to 100 billion. So the range of the values are very, very high. So now if we use both these variables in a model, the net worth will dominate it because it contains large values. Not because it is important, but just because it has large values. So one of the ways by which we can bring both these variables into the same range, so we can either standardize them or we can scale them. So now let us talk about how we can standardize and how we can scale them. So when we standardize the data, basically we mean that we're going to compute the z-values. So which means, of course, data value minus mean over the standard deviation. And here my data values are going to be from -3 to +3. Now another way by which I can normalize my data is called scaling. So here my y value is going to be, or my value is going to be my value minus the minimum whole divided by max minus min. So in that case, all values will be converted from 0 to 1. So they will be in basically in the same range from 0 to 1, and none of the values are going to be negative. So now let us take an example in which I will standardize it, and also I'm going to scale the data. So suppose here is my data set. I've got 15 observations, and now my data elements are 124, 3, 311, 341, 298, and so on and on. And my last element is 999. So the first method is standardization, which that we covered. Here we are computing the z-value. So the first we compute the mean, which comes out to be 310.60, and the standard is 309.41. So using my mean and my standard deviation, I can compute my standardized value. So as you can see, these values are -0.60, -0.99, 0, 0.10, and so on and on. And so as you can see, these values are going to vary from -3 to +3 because these are the z values. Another way I can do this thing is I can scale the data. Scale the data means my data element minus a minimum divided by max minus min. So as you can see, let's take the first example, which is 124. Now what is the minimum value here? As we see, it is 3, and my max value is 999. So I'm going to take 124 minus 3 whole divided by 999 minus 3. So this gives me the value of 0.12. So this way, all of my values can be now scaled, and as you can see that my minimum value was 3, basically becomes 0, and my maximum value, which is the last observation, which is 999, is going to become 1. And all the numbers are going to be in between 0 and 1. So this is the way by which I can scale the data from 0 to 1. So now if we have to compare the standardization and scaling, which one is better? Most of the time people used to compute the standardized values because the scaling usually becomes very ineffective in the presence of an outlier. If you have an outlier, then most of the data will get squeezed between a very small range, and that may not be very effective. So that is the reason we always compute the z-values. That is usually the better way to normalize the data. So that is the end of this lesson. Let me summarize what I covered. First of all, I covered the measure of central tendency, which is mean, median, and mode. Then I covered the measure of dispersion, range, variance, and standard deviation. Then we looked into empirical rule, standardized values, standard normal distribution. Then we looked into the measure of position, which are z-score, percentile, and quartiles. Then after that, we saw the 5-number summary, which is also called the box plot. And in the end, we saw how we can normalize the data where we have a choice between computing the standard values or doing the scaling between 0 and 1. Thank you.